a little later getting here than I wanted to be. And let's see, I think we're going to need to start at this slide. Okay, so we'll go from current slide. All right, as far as announcements go, I don't know if any of you ever tried to get in touch with me, because I'm guessing most of you work just about all the times when I would have office hours, but I do have a few changes this week. A couple of these are temporary, and one is a big change. I had a doctor's appointment yesterday, and I had to miss 45 minutes of my early class and then the whole second class. Okay, so we did start the first class 15 minutes early to take care of 15 of those 45 minutes. And this is Ashley. Okay. All right. So tomorrow morning I'll be starting 15 minutes early again. So if you were going to try to get in touch with me between 8 and 8:30, which is when I usually come in before 8, first class starting at 8:30, you got to do it between 8 and 8:15 because I'll be in class from 8:15 and on. Now the second, and that same thing will happen next Tuesday. Next Tuesday I'll start 15 minutes early again. That'll be my 45 minutes. We'll be caught up there. In the second class that missed completely, the class and I decided, let's try for 9 o'clock Friday, day after tomorrow. So normally I'm on the Birmingham West campus on Fridays. This time I'll be on Bessemer campus because that's where that class meets. And if I have to come back, either come by here on my way in to take care of things, or after the class go back by here, I'll do that. Otherwise, I'm going to stay on Bessemer campus the whole day. I'll find out from my boss. I'm pretty sure that second mini-term contracts are due then, and there's just a variety of things, so I may have to wind up coming over here. If so, I will, but if I can get away with it, I'll stay on the Bessemer campus, because otherwise, that's 30 minutes of driving that I don't get anything done. And if I have to go twice, then that's an hour of driving I don't get anything done. So I hope to be able to stay on Bessemer, but we'll find out. So if you can't catch me on one campus, try with the other. But know that I won't be near either phone from 9 to 10:15. And then there may be other times I'll be driving, so I won't be near a phone. So just try periodically, and if you can't catch me, try again a little bit later. But don't try between 9 and 10:15. Okay. Okay, the permanent change to my office hours, or for the rest of this term, is the fact that last week we were on the first mini-term. My first mini-term class, physical science class, started at 1:15. The one that started yesterday starts at 3:15 because it has some automotive students in it. Their block schedule goes until 3, so I couldn't start the class until 3:15. So therefore, on Tuesday, Thursday, now my office hours are 11:15 till 3:15. Before it was till 1:15, now it's till 3:15. Of course, the downside of that is I'm here until 7:45 on Tuesday, Thursday evenings. But that's over there on the Bessemer campus, and actually I don't leave until 8 or later, because by the time the class is over at 7:45 and I get everything shut down and set up and stuff, I'm running later than, it's more like 8 o'clock. Okay. Any questions on anything we've covered so far? All right. We are on page 335, which is in chapter 12, talking about matter. And I believe that we are in section, this is a section with lots of examples, and we did most of those, 12.5, density. Okay. Now, we had just introduced a new concept, and that was specific gravity. Does anyone remember what specific gravity is? It's the ratio. Okay, let me get my pen back. Okay, specific gravity is the ratio of the density, and usually it's mass density, okay? And this book uses D sub W, doesn't it? Yeah. It's the density of the material, so rather than saying this M is going to stand for material, divided by the density of water. Okay? Now, whether you're dealing with mass density in the SI system, weight density in the U.S. customary system, no matter what units you're using, the ratio of this is going to come out to be the same for any specific material. Water, iron, lead, something, that ratio. See, if you're using different numbers, they'll have different densities, but different systems of measurement. But when you go to specific gravity, it all balances out, and these will be the same. And what's really incredible, well, not incredible, but it's characteristic of them, the number you get from the specific gravity, if you put grams per cubic centimeter on the side, that would be absolutely correct, because that number is the same value. But specific gravity has no units, but the mass density in grams per cubic centimeter is precisely that same number. Why? Because the density of water in grams per cubic centimeter is 1. Okay? 1 on the nose. So that is the same number. So in general, the specific gravity of water is 1. Is exactly 1. 1.00, you can put as many zeros as you want. Remember, specific gravity has no units to it. A material that's denser than water will be greater than 1, and the material that's less dense, okay, than water will be less than 1. Okay? These will sink in water. These will float in water, okay, or on water sometimes, okay. Now, one device that is used to measure specific gravity is called a hydrometer, H-Y-D-R-O-M-E-T-E-R. All right, here's our other Jennifer. Okay. Why is that here? Oh, it's stuck to the back of my book. All right. Takes me a minute to get my pen to operate. Okay. Jennifer Addison is here. I keep wanting to call you Jennifer Aniston, but I know the difference. Okay. All right. All right. Now, this is a sealed glass tube weighted at one end so it floats vertically in a liquid. Any liquid you happen to have. And when it floats vertically like that, you can read on it at the meniscus of the liquid, you can read exactly what the specific gravity is of that liquid. So that's a device, hydrometer. You would think hydro means water, and it quite often is used. Does anyone know one application of this you may have actually seen someone used before, but you may not have realized what they were doing? Have you ever seen anyone stick a device into your, say, battery, into the liquid in your battery? That probably is a hydrometer measuring the density or the specific gravity of your battery fluid. If it's less than something or another, it's probably the battery is going to be going weak. More often they stick it into your radiator water to see if you have enough antifreeze in there, okay? So you will see those used for a variety of situations like that. The battery acid in a radiator, in a battery, and the antifreeze in a radiator, okay? So let's see if, seems like maybe the next slide is on your, this one. Let's see if it is. What's that? This is on page 335. Sorry, I should have repeated that when you came in. Let me see. Okay, that was the density that we had back It's the table that was found back on page 330. Oops, that was the last slide. So no, the next two tables. Table 12.3, specific gravities in a lead storage battery. New will be about 1.30 specific gravity. Old, when it's close to being discharged, about 1.15. Not that you'll probably ever be measuring that, but in case you do. Specific gravities for antifreeze and water solution. If you want a temperature to go down to negative 1.24 degrees Celsius, which is not that cold. It sounds cold, but that's only about 30 degrees Fahrenheit. Then you don't need any antifreeze. You'll probably make it okay without that. But if you're going to get down around 28, 27 degrees, you probably need it to be at least 1.01, and then it keeps on going down. Negative 51 degrees we would not need here at all, ever. That would be 1.08. About the coldest we would ever need is the one that says about negative 19.82. That would probably be more than we would ever need, and that would be 1.05. But if you're up in Minnesota or Alaska or somewhere, you're going to need to be less. Okay? Wow, I didn't realize we were this close to the end of the chapter. Here are some common liquids at room temperature, because temperature does matter. 20 degrees Celsius or 68 degrees Fahrenheit. Benzene is 0.9, ethyl alcohol 0.79, gasoline 0.68, kerosene 0.82. All those would float on water. Okay? You know gasoline and oils do. If you've ever seen an oil spill, the oil or gas floats. And that's what makes that sort of multicolored sheen on top. You can tell if there's oil or gas spill. Some denser than water, mercury 13.6, way denser than water. Seawater 1.025, a little bit denser than water. Sulfuric acid 1.84. That's what's in your lead storage batteries, but you don't have pure that, you have water mixed with it. Turpentine was again less dense, 0.87, and water is exactly 1. All right, with that we have now finished exactly 12.5. Any of those odd number exercises, 1 through 37, I guess. Any of those would be good. I think I'd break it down a little bit more. I'd say 1 or 3, either one of those. 5 would be a pretty good one. Any of the odds 7 through 23. Then any of the odds 25 through 29, and any of the odds 31 through 30 or 33, and then either 35 or 37. You choose which ones you would most like to do. And that does finish the chapter. The formulas are given on page 339. Your review questions are good for concepts, but the review problems are much closer to what your test questions are going to look like. And even though all their answers are in the back of the book, I think, no, are they? And only the odds. All of them, right? Okay. For review problems, that would be any of those 1 through 20. Sorry, I can't read. There's applied concepts that you can read if you'd like. And I think that's it for chapter 12. And I also think that I probably passed out to you the test last time, those people who were here, didn't I? So those people who weren't here, let me get those to you. And now we're moving to chapter 16. Let me get my book on the right page. All right. And let me find the test. I think I have enough copies run off. And I'll apologize ahead of time. I've got all your tests graded that you've turned in so far, but I don't have all the grades on Blackboard yet. I have hit a time in the term that is just really crunch time. Okay. Now I believe all right. This test, the first question starts a force of blah, 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 right? I think that's the question. So anyone who did not get the test last time, let me know. Did you get it? You got it? I think you got it. You got it, right? All right. I made the corrections on it, but let me reemphasize those. Okay. Number 3 is the main one. Number 3, the vertical steel columns of an office building each support a weight of 50,00 pounds. When I read that, I said, what? I didn't know if they had the comma in the wrong place or what. When I worked the problem and found out what it was, that was 50,000 pounds. They left off a 0. So I wrote a little 0 there. That's what it means. 50,000 pounds. Okay, the rest of it's right until you get to the B part, and that's 60,000 pounds. Okay? Now, let's see if there's any other issue here with that. I think the rest of them are okay. All right. I found some errors in the keys, but that won't affect you. I've found those errors and corrected them. All right. Now, let me escape there and there and go to this and 16. Okay, if you got the book, we'll be doing the next 4 chapters in a row. No more skipping. 16, 17, 18, and 19. Won't do all of 19, but we'll do parts of it. All right, so here's chapter 16. Let me get started from the current slide. And here we're going to be talking about wave motion and sound. Sounds like a good thing to do for people going into sonography, right? That sound. So that's why we're focusing on this. And we'll start with the characteristics of waves. Now, I don't know what you think of when you think of waves. Do you think of the beach, water waves? If you do, it's not a bad thing to think of because we typically represent them like they were water waves. But guess what? It can be any kind of waves. Sound waves are not just like water waves, but they have the same characteristics. Electromagnetic waves, not like water waves, but they still have the same characteristics. So we can visualize waves in the same way we picture water waves. And what we talk about is wave motion. All right. Now, with wave motion, and what waves do is they transmit energy. But there's different kinds of waves, and they transmit it in slightly different ways. So we will be talking about those. Like I said, radio waves are electromagnetic waves. They transmit electromagnetic energy, okay? Whereas water waves transmit waves dealing with the potential and kinetic energy of water. Light waves are, again, electromagnetic. Sound waves are pressure waves. So what you're studying in sonography will, if it's not the pressure wave itself, it's something that mirrors or amplifies perhaps those pressure waves. So sound waves are basically a pressure wave. Now, A wave is a disturbance that moves through a medium or through space. Okay? Let's take sound waves. Sound waves are pressure waves. Pressure waves move through solids, liquids, and gases, because anything that can be compressed and refracted will transmit a pressure wave. Okay. There are other types of waves that are not pressure waves, but you call them shear waves. A shear wave is something that does like this. That's only transmitted through solids. Liquids and gases cannot support that type of a wave. Now, what a pressure wave depends on is the elasticity of the medium. And in some senses, a shear wave does too, but a pressure wave certainly does. Now, this slide is a little bit later. Let me go back to and draw. Let's see. I hate having to go back and forth between these, but just about necessary. I'll try to illustrate figure 16.1 that's in your text. Okay? Here we have a series of objects. Think of them as molecules or massive balls, whatever you want to think of them, and that they're connected by something that acts like a spring. It may not actually be a spring, but it acts like a spring. For instance, these could be chemical bonds within a solid, say. Okay? Now, those are ugly springs, right? Okay. If you were to stretch that end one, okay, extend it outward, okay, to the left, okay, then you're pulling on this one and then release it, then what it's going to do is stretch and then compress and actually go closer. It's going to come out here and then compress to there. And that's going to move the wave, the energy down this way. That is a compression wave. When you stretch and compress this one, it affects that one and affects this one, and the wave moves down here. Each of these individually compressing and refracting them. Okay? That's a pressure wave. Now, I'm up here talking. How is sound wave a pressure wave? Well, if you hold your hand in front of your mouth when you're talking, you will feel little spurts of air. Okay? Those are compressions and rarefactions. Compression and rarefaction. Those are being transmitted through the air molecules to your ear, and your sensitive little eardrums are vibrating in response to that, and you're hearing what I say. Then the complex system of how your brain works is transmitting that into sound that you can interpret and understand. Those are pressure waves. Okay. Now, a pulse is sometimes what I did to that first ball or whatever, molecule, whatever it was there. I said I pulled it outward and then released it, and it started that action. I could have pressed it this way and released it, and then it just does it in the opposite direction. Okay? It compresses first and then rarefacts. And then that gets transmitted down. Okay? What I just described there is what we call a wave pulse. One individual thing. As I'm talking, I'm sending out dozens of wave pulses, okay? But that single one is a wave pulse. That's some type of disturbance to the medium, okay? It's, in the book, they call it a non-repeated disturbance that carries energy through the medium or through space. Okay? Now, let's think about going through space. Space has no molecules, or not any to speak of, so sound would not travel through a vacuum. at all. Okay? So in space, you don't have any sound waves. You have to have a medium there. Solids, liquids, or gases will transmit sound. Space will not. Electromagnetic radiation, however, actually travels better through space, where you're in a vacuum, than where you have air molecules that interrupt and they lose energy. Okay? The waves lose energy. So the medium is important because the type of radiation, wave motion going through it will interact with that medium in various ways. Now, when I said a shear wave, another name for that is a transverse wave. Okay? And I'll try to draw the figure that's figure 16.3 that's in your book. Here we have a wall here with a tight cord held with tension here. Now what you do to this cord is go up and down with it. Now let's go back to this wave, the top one. Notice that the motion of the wave action is back and forth, but the wave travels in that same direction. We call that a longitudinal wave because the disturbance is a back and forth motion and the wave travels in that same direction. That's why in the same length, longitudinal. Okay? Transverse wave, now I can remember doing this as a kid. I used to get such pleasure out of doing it, I don't know why. When we had the hose strung out on the ground for some reason, watering something or something, I like to get the end of the hose and do this to it and watch that travel down the hose. That look that I did when I did that. What that is a transverse wave. The motion is up and down, but the energy, the wave pulse, travels perpendicular to the motion. That's a transverse wave. What I called earlier a shear wave or a transverse wave. Okay? Again, the pulse is the action that disturbs the median, but the transverse wave is a disturbance in the median in which the motion of the particles is perpendicular to the direction of the wave motion. Wave motion is that way, the particle motion is up and down. Okay. Now, so here's what we do here. Take this and go up like this, and what you'll see is that motion travels down the wave. And sometimes when it hits the wall here, it inverts and travels back. The hose on the ground didn't do that, because it wasn't far enough, it wasn't tense enough. But you have one pulse, and you see it snake its way down the hose or the thing here. So it moves. In the book, you'll see they drew several of these, and they show the pulse moving down the wave, and then when it hits the fixed wall, it inverts and comes back to you in an ideal situation. Okay? Actually, sorry, they're showing two moving pulses, but one of them you go up, one of them you go down. That's what they're showing. But quite often when it does hit the wall, it inverts and comes back. That's not what they're showing here. Okay. I thought it was just first glance. Okay. Now, the springs are a longitudinal wave, okay, also called a pressure wave. I use both terms, and they are. Now, here are those characteristics of the wave. Whether they're transverse waves, longitudinal waves, and really electromagnetic waves are more transverse than they're longitudinal. However, they travel through space, whereas most transverse waves will not go through even a liquid or a gas. Okay. So here are some of the characteristics, and I will use this slide. Okay. Let's do this and that and that. Okay. From current slide. All right. This characterizes, these are some of the characteristics of a wave. Now this obviously looks like a transverse wave, but the concepts work for longitudinal waves as well. Okay? Unfortunately, they don't have everything listed here. But here is more of a transverse type wave. Okay? you have an up, a down. Here's the equilibrium position. Everything is pretty much measured for equilibrium position. This is called the crest of the wave, the trough of the wave. Crest, trough, and here it happens to be at its equilibrium position. Okay. Now, what the amplitude of this wave is the maximum displacement either up or down. But it's always a positive number. Okay? So the measure of this crest or trough, but keeping it a positive number, that is the amplitude of the wave. Okay? The definition given in the book, well, they didn't get to, oh, there it is. The amplitude of a wave is the maximum displacement of any part of the wave from its equilibrium or rest position. That's the equilibrium or rest position. The maximum displacement from that, either down or up, that is the amplitude. Now you might say, how do you do that in a longitudinal wave? That's the maximum compression or the maximum rarefaction. Just imagine that you took that and drew it as a curve like that. The maximum displacement, that would still be it. Amplitude. Okay. Now, just to give an idea, loudness depends on amplitude. And I said loudness, I got louder. You notice that means the compression is greater, the rarefaction is greater, the peak would be higher or lower. Okay, that relates to amplitude. Okay, the second feature is called the wavelength. Pick any point on the wave, usually the crest or the troughs, or crest or troughs or whatever. Pick one crest to another crest, the next adjacent crest, that length would be your wavelength. Okay? You could pick a trough to trough, same length. You could pick one of these points here on the equilibrium, but it can't be equilibrium to equilibrium. It has to be both equilibrium and going the same direction. So here to here would be a wavelength. That would be half a wavelength. It's a lot harder to pick a point like this. It can't be that point because that's going a different direction. It would be this one. That's not half a wavelength there. This would be one complete wavelength. So most of the time we use crest to crest are usually the easiest, or trough to trough. But whatever, that would be your wavelength. Okay? Now, what we're talking about mostly are waves that we call not necessarily standing waves, but repetitive waves. Okay? Even if it's just a single pulse, you do this one time, there's a trough at some point, there's the, crest at one point, later the crest will be there. Okay? That would be the wavelength. How far down it went between crest and crest, even if it's just one pulse. Okay? So you have a distance thing, wavelength. But if you're talking about the time it took for this crest to that crest, that is called the period. Or it could be from this trough to that trough. The time for one wave action of one wavelength, that is the period. Okay, the period of a wave. Okay? The period is the time required for a single wave to pass a given point. Now I don't really care for that definition because it's not just a passive given point. It's a particular part of the wave. This one, the time it takes for that to go from here to there. It passes a point here or here. That's not a period. From a given position to that same position going in the same direction, so we usually use crest. It's a time element. Now, so that, let me get my pen back. Okay. So distance from here to here, distance would be wavelength. And I'm going to give you the symbol they usually use for wavelength. That is a Greek symbol, lambda. Lambda length, okay? That's the distance. The time that you would get from here to here, same positions and everything else, but when measured in time, that's called the period. And quite often that's given the symbol capital T. Other times you'll see it given PER or something like that. But quite often it's given the symbol T, capital T. Little t would be just any old time. Capital T would be the period, okay? Because it is a time measured in seconds or whatever. Now, in other lives, in physics, capital T is always used for temperature. So you're not going to confuse temperature and period because you don't use them in the same context. So in this chapter, a capital T will be your period. Now, let me give you another. What we call this wave, this is a periodic motion, right? Same motion occurs, even if it's a single pulse, the same motion occurs all the way down the line. In real life, it's going to attenuate a little bit, but in an ideal world, that just keeps going indefinitely, okay? Now, nothing goes indefinitely in real life, okay? We call this one cycle of the wave, for it to get from one position to an equivalent position. That's one cycle of the wave. Okay? It could be this position to this one. Not to that one. That would be half a cycle because you see this is going in the opposite direction. So one cycle for it to go in the same direction. And again, you could pick a weird place like this, but you would have to pick the same equivalent place where it's going in the same direction on the wave. That's one cycle. Okay. So the time, the period is the time per cycle. Time per cycle, because it's going one cycle. The reciprocal of that is, and that would be in seconds per cycle. The period is usually measured in seconds. It could be a longer period, but most of the time it's in seconds. Okay? And that would be seconds per cycle. But a cycle really isn't a unit. It's just one complete do-over, okay, until it gets back to where it was before. Now, if you do the reciprocal of the period, this is called the frequency. And that's measured in cycles per second, per time period. So this is seconds per cycle. Invert that and you get cycles per second. That's your frequency. Now, frequency, because cycles isn't really a unit, quite often frequency is given in units of per seconds or seconds to the -1. You know, on your calculator, something to the -1 is usually 1 over it, right? That's what it means, okay? Now, since that's sort of an awkward unit, a per second or an inverse second, the guy who came up with it and first did a lot of work with it was a guy called Heinrich Hertz. Good Irish name, right? No, German name, okay? And so because he did a lot of the work with it, they named that unit after him, HZ. Now, 2 letters, because they had already used capital H for something in, I believe it's inductance, is measured in henries, and they had already used capital H for Henry, so they used HZ for Hertz, named after Heinrich Hertz. Named after somebody, so it is capitalized, but only the H is capitalized. They have a little blurb in your book about him, okay? That's how we measure frequency. Now, a hertz is 1 hertz is very, very low frequency, incredibly low frequency. Quite often we measure other things like your AM radios. There you're measuring things in kilohertz, thousands of hertz. If you're doing television or FM radio, you're measuring megahertz. And the mega is a capital M, capital MHZ. Kilohertz is small k, capital HZ. Okay? And frankly, there are many things nowadays that are going on the gigahertz range. That's capital G, capital HZ. A lot of your radar and microwaves are in gigahertz. Okay? And they go on from there. Okay. So I've already given you one formula, so to speak. They give it in the book the other way. Frequency is equal to 1 over the period. Okay? That shows up in your book on page 428. Where alpha is frequency, capital T is period. Now, another thing we talk about is how fast that wave is moving. Okay? And what do we usually measure speed in? What are some units? Miles per hour. What does mile measure? Distance. And hour measures time. So velocity, or wave speed, is measured as distance over time. Well, what is your distance there? Between crest? Your wavelength. Right? Okay? And the time for that same thing is your period. So the velocity of a wave, or the wave speed, excuse me, is equal to lambda divided by period. Wavelength divided by period. Length per unit time. Usually measured in meters per second or something of that nature. Okay? Could be very much faster, you know, so it'll be a variety of things. So that's your wave speed. But since your frequency is 1 over T, you could also measure it in lambda times F, because that's per second, length per second. So there's another way to measure wave speed or propagation velocity. There's a variety of names for it. Okay? V is usually velocity or speed, and lambda is wavelength, T is period, capital T is period, and alpha is frequency. So we're all set for example 1. So let's go, what did it do there? Okay. Yeah. Let's go back to our other slide and do example 1. Find the velocity of a wave. So what we're looking for, whoa, I've got to go back to my color. Okay. We're looking for velocity. It says find the velocity of a wave whose wavelength, what symbol do we use for wavelength? Lambda is equal to 2.5 meters. That's one long wavelength, folks. And the frequency is 44 hertz. What do we use for frequency? What symbol? F, okay, is 44, I'm sorry, hertz. Okay, that hurts. No, I'm just kidding. Okay. What's the formula we might use to get that velocity? Lambda times frequency. Now, what is a hertz? A hertz is a per second. Second to the minus 1. So this would be 2.5 meters times 44 per seconds, or 1 over seconds. And what would that give you? Got your calculator? 100 what? 110 meters per second. A per second, or s to the minus 1 is per second. 110 meters per second. That's moving along pretty fast, right? Not super fast, but much faster than I can move, okay? That's like from end zone to end zone, back of end zone to back of end zone on a football field in a second. Okay, that's moving. Okay, and that's a slow speed. Okay, and that's what they got in the book too. Good for them. Now, waves also, let's see, does anyone need this any longer? Got it. Okay. Let me go back to the other one, and let's see if they have this slide on the set. Oh, where was that? Oh, yeah. I went past it. Let me go from current slide. This is an example of what kind of wave? Longitudinal or a pressure wave. Here we've got your spring here, and I wouldn't be holding it like that, but that's it. And you push it, compress the spring, and then pull back, and you see the compression of the spring moves down here, and the rarefaction of the spring after the pressure, where you pull back, is here, and it moves on down. It hits the wall. That doesn't invert. It might actually bounce off and come back to you. But that is a longitudinal wave. Okay? Now, they didn't put it here for this purpose, but if you picked some value, like this first yeah, I got it. Okay. Like this one. If you go from there to there, that could represent, say, your wavelength. Okay? And the time would then be, could represent your period, and then you could measure velocity and frequency and all the things like that. That's a little bit harder to do with compression waves or longitudinal waves like this, because it's really hard to identify those. Much easier with the others, but you can have them represented that way. All right. Now here, this now is showing what I was talking about on the previous slide, one before the one we just did, a picture of the wavelength. This is a distance measurement, okay? Either from crest to crest, equilibrium position when it's going down to equilibrium position where it's going down there. Must be at the same location in the same direction. You could do trough to trough. That could be your wavelength there. Doesn't matter where you measure as long as you're consistent with it. That's your wavelength. What would be the time between this crest and that crest? The period, okay? And the reciprocal of the period is the frequency. Very good. Okay. Now, all right. We're talking about something else. We're talking about one wave, and we're going to superimpose another wave on it. Okay? These are two different wavelengths. I wish they'd call this lambda 1 and lambda 2, because obviously they're not the same lambdas. Okay? Now, if you were to combine these waves, you can see they both start here, and that's what they do here. So you add the waves, so the overall wave goes way up here. Okay? But this one starts decreasing while this one's still increasing. So somewhere about the middle here, you reach the peak of this one. And then they both start going down, so obviously it goes down. This one goes way down here. This one's still somewhat positive, so it doesn't reach the same lower point. The trough is not as low as this trough. This peak is higher, the crest is higher than either crest because they're combining. And then it comes back, and of course, where they cross each other, here, that's got to be a zero. Okay? Got to be a zero. But here's another place where a zero, where this one up here is equal to this down here. So there is an equilibrium position, but where they cross on the equal, that's got to be a zero. Here again, you have this one's so far up here, this one's equal distance down here, so there's another zero here. Doesn't quite look like it, but it's pretty close. But then they superimpose down here, and now you have from here to here is the new wavelength. Okay? When these two superimpose, now you get those are your major crest, and your minor and your major cross would be here. Your minor trough would be here to here, minor crest here to here. All those are the same distances. Okay? Those could each be used as your wavelength. Okay? Now, the reason this grows taller here is what we have here, what they call constructive interference. Anytime the two are on the same side, they're adding together, and that's they're interfering with each other, but in a positive way. Here, where one is up and the other is down, that's destructive interference. So you're subtracting one from the other. Down here, it's constructive again, and over here, so anytime that they're reducing one another because one's up when the other's down, that's destructive interference. Okay. Now, yes?
So, when is that done, the superimposing?
Okay.
When do you see that?
Okay. In a short method, all the time. Okay. For instance, I don't know if you've ever heard it when you are imposing one sound on another sound, and especially if these are pure sounds, you actually hear sort of a beat come out of it. That would be superposition, because they're different sounds are at different wavelengths, and when a lot of times they're all crossed up and you can't really tell them. But you can actually, if they're pure sounds at one particular frequency, like hit two tuning forks at the same time, you'll hear the sound go up and down and up and down. You know, you'll hear the difference there, and that's called the beat frequency. This would represent the beat frequency, different from either of those frequencies. It would be yes.
So is that kind of how noise canceling headphones work?
How what?
Or is that similar to how noise canceling headphones work?
Yes, exactly. What they're doing is specializing on the destructive interference. When the noise around you is going up, they try to invert that and add it to it. And you're absolutely right. I hadn't thought of that. My wife loves those things. Okay, when she's on an aircraft or something like that, she wants to sleep and the noises bother her. So, and she says something that someone sometimes snores. I don't know who she's talking about, but anyway, she likes noise canceling devices for that too. Okay, so, but those would be one illustration of that. I have never been any good at this at all, but these people who tune pianos and guitars and things like this, they hear that subtle little beat thing, and that lets them know when they get right on the note. You know, then they superimpose perfectly. Okay. All right. That may not have been the best answer to that, but that is one, and yours is even better. Okay? Now, next topic they're going to talk about, and we'll see if they have this one. All right, this I think is much further down the road. Or not. So I don't even see this. So nope. All right. This slide, I don't know where it shows up. 16.7, it's supposed to be. Oh, there it is. I just didn't see it. I looked on the right-hand side of the page, not the left. Okay. Okay, so this is heading toward what the next topic is. and that is what we call standing waves. So waves can superimpose, and you get some constructive, some destructive interference there. And by the way, this is an example of it in some senses. When you see that spectrum of color, say when someone has spilled oil or gasoline on water, and you see the colors that show up there, that's an example of these various things, because the different colors represent different wavelengths, and you see some are constructive, some are destructive, and so you get different colors shown there. And that rainbow of color almost you see is because you're seeing different places where one frequency will be overriding the others. Okay. What's that? Yeah, it is. It really is. Okay. So let me do a little bit.
This may not be a related question, but I just went on a field trip with my sixth grader yesterday to the DeSoto Caverns, and you know, in the rock formations,
right,
some of them very much look like waves. Is there anything going on there that relates to what we're talking about? I mean, does that have anything to do with waves?
Okay.
I mean, I know it wouldn't
right,
sound, but
right. Well, actually, sound is not a bad description there. I want to go to the DeSoto Caverns. I've never been there.
They're really amazing.
They really are. They have stalagmites and stalactites, and those are the things that look like the waves. Is that what you're saying?
Correct. Well, actually, on some of the stalagmites, they're really, you know, and I've learned you have to have a stalactite for the stalagmite to grow up,
right,
you know, together. So there's some that actually will come together.
Right.
And it looks like there are
yeah,
you know, formations that
right,
look like waves in
right,
that rock.
I'll say it this way. When we're talking about waves, you're basically talking about something, and this book probably goes into it in a different chapter. I hadn't brought it up yet. What you're talking about is simple harmonic motion. And think of harmonics, you think of music, you think of things like this, and most of nature follows some sort of a pattern in simple harmonic motion. So in some sense, you're right, it is following a pattern. And that, in a strange way, is like a wave pattern, but it's just a lot of nature. If you think day, night, temperature, seasons, they all follow patterns, okay? And the stalagmite and stalactite formations there, in a sense, are following some sort of fairly regular pattern. Not quite the same, but awfully close to it. Now, let's go back to this one. Here, I assume that most of you have been to some type of a musical presentation, and if you've ever gotten early, I'm thinking mostly about a band type thing, especially a big band, as in a symphony or things like this. And if you've ever gotten there early and you hear them all sort of tuning their instruments, doesn't sound too good, does it? It's going, you know, very cacophonous, okay, not very pleasant sounding. That's what this is describing. But once they get them all tuned and then they start playing, now they're symphony, and the sound is beautiful, okay? What you have there is going from almost random, awful, sounding things to something that we call a standing wave, or something very close to a standing wave. In one special case, two waves combine so that there is no propagation of energy along the wave, and it just sits there, okay? And they reinforce at the same places and cancel at the same places, so you form a standing wave, because the two waves of equal amplitude and wavelength do not appear to be traveling. Okay, so here we have an incident wave going in, the reflected wave coming back that I talked about before. And if you can imagine superimposing those on each other at just the right frequency, then you get something like this. And this is indeed what you have when you're playing a musical instrument. Does anyone play a guitar? No. Okay. Ukulele? Violin? Any of those? Or piano?
I played a trombone in high school.
Okay, a trombone, okay? Now what you're dealing with there is a length of a pipe, and what you're doing when your fingers are opening and closing valves, you're creating nodes in various places, and I'm sure you never hit a wrong note, or one that just wasn't even a note. I used to specialize in piano on the cracks, be in between, and or when I'm singing, I really hit those cracks well, That's no note I've ever heard of, but when you are on that, let's think about the guitar. When you finger the frets, you're creating different waves because you're changing the length, so you're changing the sound that's producing that, okay? Now, when they go to tune that guitar, they're changing the tension. More tense, less tense, okay? And that gets them right on, so the frets are hitting the notes right on the money, okay? So, this is what is happening. These are called standing waves, and that's exactly 1/2 wavelength there between the two ends there. This is one wavelength, but it's superimposed by another one, and you form a standing wave, and that is right on that note. Here's 1.5 wavelengths, okay, and this is 2 wavelengths. So your length of your bar there, or whatever fret you happen to be on, that designates, that's this L length, English letter L, and these are the wavelengths, lambdas, okay? And this is exactly, when this L is equal to 1 wavelength, you get that standing wave. When it's 1/2 a wavelength, you get that one. Now they didn't draw the dotted line here, but you could have drawn the dotted line there. I don't know why they didn't, except it's not a complete wave, is what I assume. Okay, so that's illustrating the standing waves when you hit those notes right on the money. You've got it tuned correctly, okay? If you've ever heard someone playing a piano that was a little bit out of tune, you can sure tell, okay? These are not quite the sounds that you need to get out of there, okay? That's just sort of a definition type thing, nothing problem solving, but those form your standing waves. Now, waves also, sort of like we saw before, they interfere with each other, okay? We call them constructive interference or destructive interference, but they do interfere with each other. Now, let's imagine that you had some sort of vibrating device, and you had in a pool of water, and you had one here and one there, vibrating. Same frequency or different frequencies, whatever. These look like the same frequency. So they're sending out waves at the same time, and it's the same speed, but they're a distance apart from each other. So some places they reinforce each other, and some places they cancel each other out. Okay? And that's what this. If the nodes are lining up, there's zeros there, like there and there and there. The nodes are actually at the same points there, and other places they're maximum interference or constructive interference or destructive interference. The nodes, these are sort of these imaginary blue lines that you see here, and it comes from those different nodes, okay, the lines of the nodes. That's called interference. And then they also introduce this concept of diffraction, okay? So So interference, let me give you this definition from the book. When true troughs cross, the water level is lower for one than one alone. If the trough crosses at a crest, the water level is nearly equal. Okay? That would be your nodes. Okay? And that would be one example of wave interference. Okay? Exactly canceling out the other. Now, diffraction is the property of a wave that describes its ability to bend around obstacles in its path. Okay? Now, I don't think we have a figure that illustrates it. Well, we do. Okay? Here is a wavefront coming in down this way. The sound waves are basically almost parallel to each other. But you have something going on here that you have a block here and a block there, but an opening in the middle. So this wave comes down and just keeps on traveling, but this one can't travel that far, and the wave gets bent. Now, are they this perfectly pretty? Probably not. But now you have, this is called diffraction, the bending of those waves because of the obstacles there. Okay? Now, you can see this on the seashore sometimes. If there is a, what do they call those? A seawall, a jetty, or something that's sticking out there, the waves come in almost parallel, but when you have something blocking it, then they sort of bend around that. Okay? Same thing happens on the beaches. If you have different depths, you have wave diffraction there. So some type of an obstacle in the way can adjust that. And if I'm just making a guess at this one because I'm not certainly not a musician by any means, but those musicians that sort of slide their fingers up and down the string to make a differing noise, that's kind of like the bending of a wave. You're not hitting those notes perfectly on, but sort of doing. I think jazz musicians are notorious for getting all these different variations in sounds out of that, and done well, it can be quite appealing. Done poorly, it's less so. Okay. But that's diffraction of waves. Basically, diffraction is a bending. Most of this is just nomenclature now. We really, except for the frequency, velocities, and stuff like that, we haven't hit too much that's all that quantitative yet. Okay? We will hit those a little bit later. And actually in the text, here we have it. This is what I was trying to describe. Here are the almost parallel waves coming in from the ocean. And you have a seawall here that just allows the passage of ships and things like this to come in closer, but protecting the coastal area from getting battered by the waves. Then you see, and this again is a picture, it's not, a drawing, it's not an actual picture, but you will see that kind of bending, that diffraction going on as the waves hit here, but then get interfered with on the edges, and you get that kind of a wave pattern motion, and that's your diffraction. Okay. This is illustrating, okay, have any of you been to Splash Adventure, or whatever they call it now? Do they have one of these wave pools that creates a wave? This is how they do it, okay? Is it pretty much fun? Huh? Yeah. My mother-in-law used to love to take the grandkids, she lives in Huntsville, up to Point Mallard or something like that. And supposedly there's a really nice one there too. And it may be exactly the same as they have there. I've never been to either place. But there they actually This is a picture then of the people playing in the wave pool. The energy is created by, mechanically, it's not all that natural. Now, when my wife and I were in Munich, and we've been there a couple times, we have good friends here in town, whose parents, the guy's parents live in Munich, and they've hosted us a couple of times, and they'd like to take us to this place where they built this park that's called the English Gardens, and why they call them that, I'm not sure. And there used to be a creek running through there, so they diverted it and put it through, and then there's a place where it comes up, and so much water comes out so fast, they didn't intend to do it, but they have people surfing in Munich, way far from any ocean whatsoever, because the waves come through like this, and it's a narrow little channel, no wider than, in fact, less wide than this room is, okay? And they have created these surfable waves, and people are there surfing as much and as far as they can in just this little channel that they have there. So a lot similar to these guys trying to do body surfing is what they look like they're attempting to do here. Okay. Yes?
Like the current of a river, is a current measured in, is that waves, like the length of a wave? Is that how, do you measure it that way?
Yeah. Most of the time, the waves you see, there could be some waves that are very close to the speed of the river. They don't really have to be, because the river doesn't travel at one speed. Usually it's fastest in the center and slower around the edges, a lot of the same way that this is, where it is able to come through unimpeded. It's going faster, and it's slowed down wherever there's that edge friction. So it's sort of hard to do, but if you were to measure the wave fronts here, you would have a different speed from the wave fronts there. So in a sense, if you were right near the center of the river or creek or stream, whatever you're doing, and measuring those waves, that will give you the closest to the velocity of the river. But it's going to slow down around the edges.
Well, I asked because we were just recently somewhere where they had created a lazy river,
Right.
A resort, and
Right.
and I thought, I kept trying to figure out, now how does this work? I mean, I guess there's some kind of jet that propels the water, but I guess they have to decide directionally,
Right.
which way they're gonna direct. You know what I'm
Right.
saying?
Now, sometimes people have done the reverse, and generally to a negative consequence. If you ever looked at a close map of the Mississippi River, it does like this as it's coming down. It isn't just going like that. That's nature's way of doing it, and you really shouldn't mess with Mother Nature, okay? Sure, it floods some and stuff like this, and people think, well, if we straighten that out, we could have faster transportation down the river, we could get our supplies, we could get trade sped up, all like this. But every time they've tried to do that, they wind up messing up because they speed up the river. That there is a reason it meanders like that. And once you start cutting that off, it goes faster, it erodes the sides, rather than building up the sides, which a meandering river will tend to do. So they did this in the Nile River in Egypt. They decided to put the great Aswan Dam way up there to generate electricity, because Egypt didn't have any oil like many of its neighbors did, so they were going to create their electricity with that. Good idea, but in the process of doing that, they messed up downstream, and now the floods that they were trying to eliminate, they were the same things that produced fertility to the soil on either side of the river, and that's what made the farming really great along the Nile. When they cut that out, the land went really poor, and people couldn't make as good a crops. Duh. Okay. So just about any time we mess around. But then it sounds like what you're doing, they are planning the things to try to create a certain effect. And they have got that kind of stuff down pretty well. But just don't mess with Mother Nature. There used to be a commercial that did that. You know, I can't remember what they were advertising. Okay. Now, let's move to electromagnetic waves. These are waves like light waves, radio waves, gamma radiation, I mean harmful stuff, good stuff, bad stuff, anything that is electromagnetic radiation. The same equations we had before, I think I'll write it here. What did we have before about the velocity of a wave? What do we have there? Do you remember that one? There were two formulas actually. Second? Okay. Second? Wavelength over period, or another way to wavelength times frequency. Okay? Now, that's the velocity of a wave. Now, there's something special about electromagnetic radiation. All electromagnetic radiation travels at the same speed, and that speed is the speed of light. So you could take that formula there for electromagnetic radiation, and instead of V, it's C. And C is equal to lambda F, or C is equal to lambda over period. Okay? Most of the time we deal with frequency rather than period. Okay? It is the same formula, but the thing is, this velocity could change. This velocity never changes. The speed of light is a constant of nature. So now you don't need to know two things. All you need to know is one. Either the frequency or the wavelength, and you can calculate the other. Always. Okay? Now this is showing some of the frequencies. I'm going to it's all right to erase that I just did up there. Well, let me just erase some of it, because some of it's interfering. Destructive interference here. Okay. Okay, that's okay. I'll just give you a few characteristics here. All right. Now, electromagnetic radiation, the frequencies are typically very, very high. Okay? They start here at 10 to the 4th cycles per second, or just per seconds or hertz. That's already in the kilohertz range. This is 10 kilohertz, 100 kilohertz, 1 megahertz, 10 megahertz. Okay, so that's what you're dealing with here. So your AM radio waves are down in this range. Because a lot of those, 100 kilohertz or something like that, 107, 90, those kinds of things. Okay, that's your AM radio. Okay. I think when they saw, say, broadcast band, I think that's what we call the CB, Citizens Band. Many years ago, probably before y'all were born, there was a big, there were a lot of songs about CB, and everybody was on Citizen Band, and it lasted maybe 4 or 5 years and then died out, okay? It was really big, okay? And they call these short waves here. I don't know why. But then your FM and TV are along in this band. Microwaves are here. You would think those are really short to be called microwave. Okay. Now, if your frequency is that high and the frequency times wavelength equals that fixed constant C, and these are actually low frequencies here, those are going to be very long wavelengths. So here your wavelengths are 3 times 10 to the 4th. That's 30,000 meters, okay? 300 meters, 3 meters, very long wavelengths. Okay, now think about this. Have y'all, I know you've driven by Red Mountain, right? And you see all the antennas there, okay? Some of those, they're not this long. Some of them may be between 300 and 300 meters long, okay? That's because those are the wavelengths being transmitted. Your radio towers, those are some fraction of the wavelength. So your radio towers that are sending forth signals, that's why they're so tall, because you're very long wavelengths, okay? Now, they also do TV signals and stuff from there, which would be much shorter than that, but they want to get those towers as tall as they can get them. So even though they're not using the whole length of the tower, you want them as tall so they can reach as much audience as possible. Okay, so there's a couple of reasons for that. Now, your cell towers, if you'll notice where those are located, usually on hills. Okay, the Italian kid that lived with us one school year went to Altamont, which is up on top of Red Mountain, basically, and Altamont leased out part of their land to a cell tower. They built a cell tower there, so that gives them revenue, okay? Because they're way up on the mountain, might as well take advantage of it, okay? And if you'll notice driving along the expressway, when you get to a real tall hill, there will be your cell towers. Because those are usually microwaves, you don't need that big a longer thing to do, but you get them as high as possible so they can transmit those in all those directions they do. Okay? So these are your low frequency, that 10,000 is considered a low frequency, up to, goodness gracious, 10 to the 19th. Those are your very high-powered gamma rays. These are deadly. X-rays can be deadly, used in a proper controlled format. They usually don't do that much damage, but they can. And that's why the X-ray technicians wear these lead aprons before they ever turn on the machine. They're back behind a wall, right? I guarantee that wall has lead in it to protect them from that radiation. Even the dentist, when they're doing your mouth, before they turn on the machine, they're in another room, doing it from there. Looking through glass that is sort of dark glass, leaded glass, okay? Thick leaded glass to protect them from even those X-rays.
What about the ones they use the little thing they put, up against you?
Yeah.
They still doing the X-ray.
Yeah, but then that's shielded like crazy. Okay, it's got that little thing has lots of. If it's not lead, it's something very dense in there, protecting those from coming out. Yeah, and
they use gamma or
not gamma. Gamma is deadly.
Yeah, they don't ever use those.
Okay. Oh yeah. Okay. In certain types of cancer treatments and maybe some other tumor treatments, they have what they call gamma knives. And those are things that send out just very little but high energy gamma radiation. And it literally is cutting out tissue because it destroys, okay?
And I was thinking that like when you do radiology,
right.
I know that's not what we're doing, but when they do that, they use gamma because it goes, it does the little different levels. Yeah. I know you can use different frequencies and things like that. If that's what you're talking about, the levels, yeah, that makes sense. I'm not a very good expert on that, but I do know they have things they call gamma knives that they can go in and just a little bit of a burst of radiation can basically cut, if very well controlled, cut out a tumor and get it out of there without ever having a physical scalpel in there. You don't need anyone's hands in there, so they do use those gamma knives. Now, the ultraviolet radiation, that's the stuff that, okay, let's back off. We have this wonderful thing all around us called our atmosphere. And our atmosphere has many layers to it. Of course, the air near the surface, and then you get the stratosphere, and you get the thing. And somewhere up there they have what they call the ionosphere. That's filled with ions, okay? And then there are other spheres out there, and I can't remember all the names of them. But that combination of all that, see, the energy coming from the sun is one enormous, and every star is one those are incredibly enormous nuclear reactors. Hydrogen reactors, okay, not little plutonium or uranium reactors like we use to manufacture electricity here. These are many times stronger than that. Fusion reactors. And they send out all this radiation in every direction. Every direction. And space is full of that radiation. That's why nobody goes into space without those big, bulky space suits that are silvered, so they reflect most of that and probably leaded and things like this. And you don't stay out there long because that stuff will kill you. Okay? Without a doubt. But our atmosphere shields us from that. Almost no gamma rays come through our atmosphere. Very few, if any, X-rays make it through our atmosphere. Now, a few ultraviolet rays come through. And what do? What does ultraviolet radiation do to you?
Where you get sunburned.
That's where you get sunburned. They kill skin cells. Now, your body tries to combat that by sending, is it melanin, to the surface to try to block that. And that's what gives people suntans. Okay? And people think having the suntan make them look really cool and healthy and stuff. It really is indicating that you're a very unhealthy lifestyle because you're killing cells. Okay? And the sunburns are dying cells. Okay? But time after time after time of exposure to that ultraviolet radiation will ultimately produce skin cancers. This red spot here is AK or KA or something like that. That's precursor to skin cancer. I put sunblock on that every day. Summer, winter, spring, fall, every day. If I'm going to be outside, whether I'm outside or not, I put sunblock on it, trying to hold that off to keep that from becoming a cancer as long as I can. I've had one little skin cancer removed from my chest, but many years ago. I'm surprised I haven't had more. Both of my brothers and my sister, they live on the farm. They've had multiple ones taken off. My older brother actually, top of his ear, because they said they could do reconstructive stuff and rebuild it. He said, look, at my age, who cares? So he said, at one time that would have been important, not now. So our atmosphere allows in only one very narrow little band of light, and that's visible light. That's all that lets in. Blocks most of this, just by all of these, most of that. The ultraviolet radiation does make its way through. Okay? And this is what comes through our atmosphere. Thank you, atmosphere. Without you, we're dead. Okay? So you talk about, can there be life on other planets? Those planets have to have exactly, life like we know it, exactly the same atmosphere, exactly the same, and temperatures, and, I mean, to be exactly the same thing, I don't know. They say the odds are there are other planets just like ours that could support life. We don't know if they do or not. We don't know if they even exist or not, but they say so. But boy, we are very fragile. Our system is very precise. Okay, so light comes in. Now, ultraviolet radiation, all at that frequency, all at that speed, comes in at the same speed, but when it loses energy, it doesn't lose speed, but it loses frequency, lengthening the wavelength. Okay? The speed is still the same, but the frequency slows down. So here's the key. The lower the frequency, the lower the energy. The higher the frequency, the higher the energy. That's why gamma rays are so deadly. They're such high energy. Okay? It takes more juice to produce FM radio than it does AM radio. Okay? They don't go as far either. They don't bend as easily. That's why AM radio, we used to, when I was young and FM wasn't that big back then, we could pick up, what was that station in Indiana that we could pick up and hear ball games on? And all our local stations had cut down power and the AM stations ran together. There was one station somewhere out in Indiana that sent for a good strong signal. We just happened to live in a place we picked up that signal really, really well, and it was clear. Okay, so we listened to ball games on that. Whoever was playing, usually it was St. Louis, I think. So anyway.
So what did you say again about AM versus FM?
What's that?
Visualize. So what did you say about AM versus
Okay,
FM?
AM radiation is lower energy, longer wavelength, lower frequency. FM is shorter wavelength, higher frequency, but the speed is the same. But the AM radio usually will go further distances because it bends in our atmosphere. Remember that refraction that we have. Okay? FM pretty much is line of sight. Okay? So if you're in a location where this has hit the atmosphere, usually the ionosphere, and bounced off of it, you can pick up that station thousands of miles away or hundreds of miles away. The FM you just don't get. You have to be almost within sight of the tower to get an FM station. Like when we're driving from Birmingham to Atlanta, we start losing the FM stations somewhere around the state line. And then we'll start picking up the Atlanta stations because that's about midway, and start picking those up. For a while there, you're sort of dead man's land, and you either listen to some local station, or I do. My wife has her devices that she can listen to, Pandora or whatever she wants to listen to, okay, when we hit those areas, okay. So our atmosphere allows in just as little visible spectrum, little bitty spectrum here. But when it comes in and starts losing frequency, lengthening the wavelength, that becomes infrared. A little bit. Infrared radiation is heat. So it comes in as light. Now this is why it wouldn't have happened much today, but a little bit later this fall and early winter, when it can be pretty cold outside, but it's a sunshiny day but cold, you go out to your car and it'll feel toasty, won't it? Or the reverse of this past summer, if you keep the windows up, okay, and you go out to your car after it's been in the sunshine all day, it's 10 or 15 degrees hotter in your car, and that's why kids or pets left in cars can die, because they get really hot. Here's why. The visible light comes through the glass. As it comes through, it loses frequency, lengthens its wavelength, it changes the heat. But that heat energy doesn't have enough energy to get back out through the glass. So it doesn't get retransmitted out. So the heat builds up, and that's why your car gets warm in the winter or overly hot in the summertime, because of that. That's why usually on those real bright sunshiny days in the summer, if it's not going to rain, I have the windows cracked to let some of that out. Okay. Now, I don't know if any of you are climate deniers or you believe in climate change, stuff, but that's what our atmosphere, carbon dioxide, methane, and some of the HFCs and other fluorinated hydrocarbons, things they use in things like refrigerants and stuff, those are really bad, what they call greenhouse gases, because that's exactly what a greenhouse does. It lets the visible light in, lengthens the wavelength, traps the heat inside. That's what's happening in our atmosphere. The more carbon dioxide and other greenhouse gases that are in there, then more and more heat gets trapped, less visible light gets reflected back out. And that's why, theoretically, we have global warming. Okay. Now, sure, there's always been cycles, cooler, warmer, but those usually span thousands, if not tens of thousands of years to go through those cycles. What we see happening now, temperature going up at a rate that is basically unsustainable. Species can't adapt. When they're given thousands of years, yeah, we can sort of adapt to things things change and stuff, when they're happening this fast, okay, we're going to be in fairly serious trouble. In fact, we may already be there and not realize it. So that's also part of that. So energy is related to frequency, okay, not wavelength. So the higher the frequency, higher energy. Shorter the frequency, less energy, but heat, believe it or not, heat energy is lower level energy than light energy or ultraviolet. So infrared doesn't burn you. I mean, it burns your hand, but that's a tactile thing. It's not something from the radiation itself. Okay. Beat that to death, didn't I? Okay. Does that make sense, sort of? Frequency, the higher. Yeah, it's related in a negative sense to wavelength, inversely, directly with frequency. Yeah. You probably don't want to hear this. There was a famous quantum mechanics guy named Max Planck, and he came up with this thing: energy is equal to Planck's constant times frequency. Okay. I'm sorry, I mean frequency, which he used mu. That was what, I can't write. Let me see if I can get that right. Here I'm trying to say something and I'm writing everything wrong. Okay. That's the symbol they use for not just velocity, but, there's another term for it. It's not quite angular velocity, it's something like that, but that's related to frequency. Okay. And that's, on the quantum sense, that's true. So yeah, energy is related to frequency, directly related to frequency. Okay. So let's do example 1 in section 16.2, electromagnetic radiation. Okay. So let's go back to my other slides. All right, example 1. The FM band of a radio is centered around the frequency of 100 megahertz. So that represents what? Frequency. Perfect. Okay. So the frequency is 100, and they put a bar over the last zero, meaning that's good to 3 significant digits, megahertz. And again, your large thing, mega means million. And anything million or bigger, they use capital letters for that. It's not named after somebody because they've already used little m for millimeter, you know, a mu, which is a Greek m for micrometer, micrometer, okay? So to get the big ones, they use capital letters. And from there on, they use them all capital letters. Find the length of an FM antenna if each arm must be a quarter of a wavelength. Okay, so we know that the antenna, and I'll just pretend that it's, they say arm, so we'll say each arm is 1/4 lambda. Okay, so, and it may have several arms. Okay, now, all they gave us was the frequency of this radio signal. What we need to know is what lambda is. And what was our formula?
Constant equals lambda times frequency.
Say that one more time.
The constant equals...
Yeah, that's the speed of light. Okay, the speed of light is equal to lambda times frequency. We know the frequency, we can calculate lambda. By the way, I hadn't told you what that speed of light is. Yeah, they give it in the text. I should have given it back there on that slide that had it. Speed of light, c, is 3.00 times 10 to the 8th meters per second. That's the speed of light. It's a constant of nature. Okay, sort of ugly there. Okay. Now, that's a constant.
What we're looking for is the wavelength, lambda, and we know the frequency, so let's divide both sides by frequency. And we get lambda is equal to speed of light divided by the frequency. I can't get my pen to write. Okay. Or, for those of you who like to use the Navy way, you like triangles or circles? Does it matter? Triangles. Okay, I like them too. Okay. So this one. Okay, the things multiplied go down here, lambda f, and that puts the c up here. Okay. So if you don't want to manipulate it this way, just do that. So lambda is equal to c over f, just what we have here. So that would be 3.00 times 10 to the 8th meters per second divided by the frequency, which is, I'm going to write that as 1.00 times 10 to the second. 100 is 10 to the second. Does that make sense? You don't have to do that. I was just showing you another way to do it. And that is in per seconds. The per seconds, I've got to, sorry, sneeze. Poor people at home didn't know that was coming. Okay. The reason I did this, it makes the division easier. That's going to be 3.00. 3 divided by 1 is 3. And then this will be here to divide numbers with exponents, subtract the exponent, times 10 to the 6th. And that will be what you have left, meters. So that's the wavelength of that microwave. Okay? Now, the antenna arm, that's what we're looking for, is a quarter of that. So divide that by 4. So the antenna arm will be 0.75 times 10 to the 6th meters, or 7.50 times 10 to, now if you move the decimal, make this a bigger number, make that smaller, so that 10 to the 5th meters. So that's what it should come out being. Oh, they left it as 0.75. I left off a 0. You got 3 significant digits, so put it in there. Sorry about that. Something's wrong.
That's because,
Oh. This is megahertz. Sorry about that. I just did hertz. Mega is another times 10. Okay, let's back off. Sorry about that. I talked all that about the unit, but then I messed it up. Okay. Okay. The frequency is 100 times 10 to the mega means 6 hertz. That's the mega means 10 to the 6. Okay. So this is 1.00 times 10 to the second. That's what I did to begin with, times 10 to the 6 hertz. That would be 1.00 times 10 to the 8th. Because when you're multiplying, you add the exponents. Okay? Hertz. So that's what, that's what you divide by here, 1.00 times 10 to the 8th per seconds. That's what a hertz is. So that's 3 meters. Divide that by 4, and you get 0.75 meters. Okay. And this one, if you wanted to write it in scientific notation, 7.5 times 10 meters, 10 to the first. You don't have to do that. 0.75. So each of the arms there is 3/4 of a meter. Now what's a meter? It's approximately your opposite ear to the tip of the finger. So 3/4 of that would be something about that. So that antenna, the arms would be about like this. A little bit shorter than my arm. About like that. Okay, does that make sense?
Where did the 4 come from?
Oh, they gave that in the thing. They said find the length of the FM antenna if each arm must be a quarter wavelength. You see it in the problem? So that 1/4 of a wavelength, which is a wavelength divided by 4. 1/4. Do you see that as on page 434? You see a quarter wavelength. So each arm is a quarter of a wavelength. Okay, good deal. Good question. Oh, sorry, I botched that one up. Okay. Now, ooh, it's happened again. Okay, I know I brought a pencil out here somewhere. We will start next time with the we just did the electromagnetic spectrum. I should have done the example 1 earlier. So basically, we just finished 16.2. There's a little blurb there on evading radar. You may have heard them talk about a stealth aircraft. They're called stealth because it's hard to follow them with a radar. And that's how we detect things. A certain politician was saying, oh, it's hard to see these aircraft because they're stealth. It's hard to see them on a radar. Anyone can see them. They're an airplane, you know, but duh, never mind. We won't go there. Too far. Okay. What is radar? Radio detecting and ranging, and that's sending out electromagnetic radiation. It gets bounced back, and you pick up the signal, and you take half of the time that it took to there, and you know, because all the radiation is at the speed of sound, you can calculate how far the object was from it. Pretty sophisticated equipment, but it's not that bad. So you can do any of the odd number exercises in 16.2 from 1 to 17 that you choose to do. And we'll pick up next time with sound waves. That's the one we've been waiting for. So that will begin next time. Okay. Where is, oh, there it is. All right. Any questions? Good deal. All of you have your test for chapter 12. We're moving pretty nicely through 16. I only have a little bit more to go, and then we'll be, well, yeah, a little bit more to go, and then we'll be ready for the chapter 16 test. So keep it bumping along.